metal surface, the oil is flowing outwards.
It's okay.
Then we should investigate the relevant parameters and how they affect our task. So overall, I will use a scientific structure of my presentation. Let's move on to experimental observation. First of all, I measured different parameters. It was the threshold temperature, the velocity increase, the thickness influence, the oil type influence. Later, I will describe how I checked all of these observations. So possible mechanisms, I use different physical concepts. My main one is the Marangoni flow, thermocapillary flow, the Marangoni effect. Also, I'm checking the temperature-dependent viscosity, the capillary leveling, the bouncy convection, the evaporation, and thermal expansion. As I said, the Marangoni effect is the main one. So it says that when the temperature gradient actually creates the shear stress on the surface, and this shear stress causes the oil to flow. So actually, the main parameter on the Marangoni effect is the change of the temperature gradient, and also the change of the viscosity based on the temperature. So as you can see, if we have the hot center, then we have the lowest surface tension, and with the cold edge, we have a high surface tension. So our flow is moving from the center to the edge. If you look at this, we have the heated surface, so we have the temperature that is coming from the center. So that's why we actually have the main temperature in the center because of the bouncy derived convection. So the edges are more cold, and the oil moves from the hot region to the colder ones. So governing equation systems, I used the Navier-Stokes equation, and also I used the thin-film approximation so that my model and experiments would work well. I also measured the Reynolds number in order to check whether my fluid is laminar. So as we can see, the inertia is not really relevant because it's less than 1. So that's why we can use this. So I have actually the equation about the flow. So the red one is explaining the Marangoni effect, and the black one is talking about the capillarity effect. So moving on, I have authorized the stresses. However, in the presentation they are not covered. The viscous stress is the above one, and the Marangoni stress is the lower one. So when I am saying that they are equal, I have my velocity contribution. So in my experiment, I say that the Marangoni effect is the main one, and we also have other effects that affect my experiment and theory. So that's the capillarity, viscosity, inertia, gravity, and evaporation. So based on the formula that I have concluded, I could say that my model predictions are based on the temperature difference between the center and the edge, the thickness of my fluid, and also the viscosity parameters. So I also use dimensionless analysis and check different numbers like Reynolds, bond number, capillary number, Piclet, and so on. So I have used them to investigate which parameters are the most important one. And when I was checking them, I realized that the Marangoni number is the most important one, and others one are good for my experiment to conclude. So moving on to experimental setup. Yes. Moving on to experimental setup, I actually have another one. I don't like this one because when I was pouring the oil on the pan pit maker, this ruler could affect my flow. So that's why I have changed it. And how it was going, I had no, thank you. Well, maybe yes. So I have the temperature that is moving on through the center, and then I have a quick maker, and after that I used my thermal camera, as you can see there, to see the temperature gradient. Also, so when I was looking on my temperature gradient, I chose the most hotter region, and then I put the oil there and saw how there was the distribution of oil. I've used some different parameters, that's the different oils. However, oils do not truly say about the viscosity. So that's why I've used some PMAS with 210,000 in order to check the viscosity itself. So that the silicone oils. Oil types were the grape one, sorry, not the grape one, the olive oil and the sunflower. To check the velocity, I've searched the Google with my photos. So the measurement procedure, actually the main things that I have used is the center temperature, end temperature, oil thickness, oil type, flow velocity. So I have two stages. Firstly, because I do not have a truly ideal surface, I have a pan. So actually the pan has, maybe you can see the central circle, and also it has boundaries. So I have two stages. First is outward motion, when oil does not hit the boundaries. So after that, when the oil is when oil touches the boundaries, I've used the model that predicts how the pan itself regulates the flow. So it's based on the thickness, the polar angle, to conclude what point I'm using, and also the distance. So here you can see the wall-mounted motion. I say that the Q wall is equal to 0, so that my boundary condition would be okay. Also, I'm saying, well, the second one that is equal to 0, I do not do it because the cosine of my angle is not always the cosine of 90 degrees, because we don't have the equilateral spreading. So that's why I think we should change it to the cosine. Wall-mounted motion predicts how the temperature of pan and temperature of oil relates to each other. Here we can see the difference between the radius and the height. The height is, right, you can see. I think I need you. So actually I have different graphics because I have a lot of parameters. Sorry, I forgot. I also have the temperature difference. So I use different temperature like 60, 80, 100, and so on to go to the graphs. Also, I have the thickness that I've measured the area of my oil, and I will also have the volume. So that's why I can calculate the thickness. Thank you. So I actually measured the thickness. Here you can see the graphs of the temperature difference. So as you can see, I've measured the from 20 to 100. I also was interested in what will happen if I don't have the heat. I also checked what if we have different oils, as I said. Then here you can see the heat map based on the different parameters that I provide. To sum up, I checked the different parameters on my experiments and model. And the main fact of the theory is the Marangoni effect that was proved by experimental setup, experimental part.
And thank you so much. Time is over, so there's a moment for the question from the opponent. Go ahead.
Okay, so firstly, I'd like to thank you for your presentation, which was very helpful in understanding like the flow. So can you give me one explanation of exactly how flow works and which force statistics sets the direction of the oil?
So first of all, we have a heat, and then this heat creates the temperature gradient, or actually also when convection creates the temperature gradient. So when we have the temperature, our tension.
Okay, so thank you. So next, like you mentioned that like you measured the change in temperature. So and also like did you verify that your heating is uniform and whether or not you account for this in your theory?
As I said, I use a thermovisor, and I have different videos. Firstly, how my heating is heating. Also about the fan.
So also you mentioned that you measured the thickness. So like you had a diagram with like a ruler. So how exactly do you measure the thickness?
How I measure thickness?
Yes.
Firstly, I measured the area of the oil, and then I also calculated the.
Okay, so but then like there could be some evaporation. Did you verify that like there was no evaporation?
I also checked the evaporation thing that I placed on the 90 degrees.
Yeah. Also, like in your theory, you had like an equation for Q. Unfortunately, it seems to be missing like this parameter that depends on gravity. So I wonder whether or not you accounted for the gravity of the liquid.
Yeah, I have it on another presentation, but I think.
And also, like the pharmaceutical says to use cooking oil. So why do you solution oil?
Because I use actually the cooking oil, the olive oil and sunflower oil. However, they do not only have the viscosity, they actually have different things that affect the experiment.
And
So
that's all. Time is over. So the time for your preparation. Go ahead.
When ion connects to the projector and it works, and then it stops working, and then it works, is it their problem or our problem?
It's their problem because it should, and it works for everybody. If you connect this, it works everywhere.
Yes, but everyone, I noticed that the other guys connected and they had disconnections.
No, it should be established with the cable.
Yes, but the cable is their problem or our problem? We provide the cable.
Yes, but they have to keep the cable on the table. And they didn't do anything. They put it on the floor.
Maybe we should tell them. Someone else will be there and
Each time he's just going there and try to process.
maybe one of the colleagues.
Okay,
Because I
will
don't think
address
it's fair to not let them present, because it's not that they didn't connect.
They disconnected this to change something in the presentation. It was not disconnected because of this, it was disconnected because they changed the
Slides, not because changing slides, because they try to do something else.
They do something on the slides and we reconnected.
Why?
I don't know, it's their job. They did changes in the presentation. So they was changing the presentation.
So, all the connectors, please keep the cable on the table. It connects, you know that it works. Go ahead. Each time you disconnect this,
2026, still we cannot connect.
okay, okay, you have 4 minutes for presentation. Go ahead.
Okay, so I'm Lucas, and I'm uploading also. So we broke down the problem as like, so firstly you had to identify the dynamics of the outward coil flux, and also you had to perform parameter analysis of how different conditions affect like the thickness and also like the radial velocity of the oil. And also you had to like analyze the conditions for a dry hole to form in the middle. So our summary of the report is that like they first they lack quantitative explanation of how exactly different forces are used to create an outward flux, like as for example during the question you faced. And also in the theory they analyze the Marangoni effect and how the temperature gradient shear stress achieves oil flow, and also the temperature equations, the compressible Navier-Stokes equation, and also did like outward flux analysis. Furthermore, they did some experiment, and it's not very clear how their heat source plays into everything. And also, in their analysis, they did not really like vary a lot. Okay, so the strengths, as I mentioned, are some points to improve. Firstly, like it's not very clear exactly how the Marangoni effect is derived. And they also need to mention the boundary conditions and like and the heat flux, and they didn't really explain the uniform or not uniform effect. And also, they didn't exactly say how the PD was solved, and whether they used numerical simulations or other methods. And they didn't really compare the theory of the experiment, and they seem to only have shown like the simulation. And also, they used silicone oil, which appears to be against a problem statement, which says like cooking oil. Okay. Yeah, and so, yeah, and so, so like maybe I'll like just move into some of the discussion. So,
Okay, look.
So firstly, in the experiment, like the heat flux needs to be characterized. For example, like perhaps you could have measured the temperature gradient across time. For example, you mentioned that you had an interferometer, and you could have used that to like measure the temperature, and that could have given you like the heat flux. And also, it's not very clear how you measure measured the boundary, like the boundary angle, also the thickness. I wouldn't suggest using a ruler. Instead, you can color the cooking oil with, for example, some dye, and then you can use some ranges to like measure how exactly the thickness changes. And also the radial velocity, that it's not very clear how they measured it. They appear to use some computer, but it's not very clear exactly what they did there. And furthermore, for a theory, they didn't really explain how the boundary conditions change with respect to time. For example, the temperature needs to be like incorporated into theory, and also their experimental stuff seems to have limitations. So like we like the reporter to like perhaps address.
Time for the discussion, go ahead.
I think we should start with the granular focus.
Can you speak loudly?
Let's start with the granular focus. We'll see how we measured it. Firstly,
So firstly, for like the radial velocity, it would change depending on the thickness that you're measuring at. So I wonder whether or not you were able to take that into account. For example, the top layer of the oil may be actually moving inwards, while the bottom layer may be moving outwards. So
so yeah, I'm saying that my horizontal
and also you measure the you mentioned that you need to account for how the different for example surface tension and viscosity changes with the temperature, right? So I'm wondering whether or not you actually measured that in practice, and whether or not everything was just taken together, because it seems that you love different kinds of oil and water.
Presentation mode.
sorry, what did you use?
Yeah, so essentially you need to measure the viscosity and how the surface tension changes temperature. So for example, for the surface tension, I might recommend that you, for example, uniformly heat the oil to a certain temperature.
I've had it.
And yes, okay. And
So actually, I had another experiment when I had uniform heated plate on the 40 degrees per Celsius, and then I put the oil, sunflower oil, and also I checked the different reaction.
okay, so did you measure heat surface tension? Because using that method is not recommended and requires full assumptions. And also going back to what you wrote for Q, you wrote Q is equal to some Marangoni term, and also other curvature-based terms, but you didn't really account for the gravity. So for example, if you have some oil which looks like this, then the gravity will push this down and cause some pressure.
So to analyze the gravity itself,
In your theory, whether or not you incorporated this term.
actually, yes. Could I have my finger out free? So yeah, I actually have two components in my flux. So I've used the gravity, and the
Okay, so also with respect to the heat flux, do you think it would have a singularity at zero radius, at the center?
What is singularity?
Yeah, and also could you show so is there a singularity for the heat flux calculation when the radius is equal to zero, at the center?
Right.
And also could you also show the experimental result again?
So you're asking me what will happen if my center is equal
Could
to?
you like please show the experiment again?
Minus. Plus.
Yeah. Yeah, no, you don't need to.
6 is 0.
You don't need to unplug it, like, so you can all see, like the graph that you were showing, like you can plug it back in.
It's not so this presentation is more like
Yeah. Yes, and also, like, I also have to ask you, like how exactly the capillary effect plays into all of this, and whether, like, there is.
So as I said, I've evaluated the different parameters. And first of all, the first experiment that I have was with the shape. So we know when we are pouring the oil, it actually has some energy and we need some time in order to it to be silent. So that's why I've used the circle and put the oil in it, waited some seconds,
No,
then I've
you already, like, I'm asking for the experimental data, but perhaps you can't find it at the moment. And also, like, again, going back to the calibration, like, how I recommend you do it is based on the previous the dye method for measuring the thickness. You can just like also integrate the thickness like over like radially, so that way you can quite get the volume and make sure it's consistent with time. And thus like they know about the saturation. Because like your theory seems like it's potentially inconsistent at times. And some places you say there's only Maragoni effect, and some other places you show the capillary effect. So, yeah.
So if you could please sum up your question.
Yes. So what is the heat flux and how does the heating up affect it? Yeah, and also for the capillary effect, essentially the idea that because the center region will be heated by the heating pad, and so that will cause a certain percentage of decrease. And the idea of the capillary effect is that it would cause potentially some fluid just essentially flow, yeah, to the region below the expansion. And yeah.
So yeah,
So yeah, like this equation over here.
this is the equation that I measured.
Also, a very key phenomenon is the dry hole, which we identified as one of the listed task requirements, and whether or not you observe that experimentally.
Yeah, I've observed it, and it was
Yeah,
on the
okay.
first line.
Let's do that.
Yeah, I do. I can show you. It was on the first line of
And also, I'd like to ask you whether or not you think your model would produce only axis-symmetric solutions, or whether or not there could be more interesting phenomena.
I think it could be something more interesting because we
Yes
actually
or no,
have
whether or not your model can produce non-axis-symmetric solutions.
yes, it does.
And so, can you show me exactly what part of your equation allows non-axis-symmetric solutions to form? Just explain very briefly what.
So I have the three parameters. I have a feeder that says what point of my oil is checked.
Yeah. Okay. Actually, no, that's not the reason. And yeah. summary, like it seems that like you're not necessarily like demonstrating all the different phenomena and things like that, missing some experimental demonstrations which are actually very important to supporting your algorithm claim.
So, half a minute left.
I actually do not agree because when I was checking all my experiments, I vary different parameters. So when I was saying that my velocity is
Also, your experimental data, like some where the have you found it yet?
yeah,
Like
I
you
did.
showed an image like just a few moments ago, like where is that? You just like opened it up again.
So firstly, I have the video how I was tracing the particles and the temperature by the supervisor. Then, for example, this graph shows the spread overview.
Okay,
of the-
time is over. Okay, so it's a time for conclusion from
Okay,
the
so
opponent.
so in conclusion, the reporter gave a merely qualitative overview of the Marangoni effect, and used the Navier-Stokes equations to derive like some differential equations that could have been solved using the appropriate boundary conditions. And they considered migrating stress, viscous stress, and also the tangential stress balance in the derivation of the characteristic velocity. But they're also like missing the inclusion of like the gravity component, and also they vary the type of oil difference and also the thickness. But like they didn't really set the graph clearly, and like we still don't really have like to be able to see it. And so we asked the question of like what boundary conditions they used, and also like what values they meant, like viscosity and surface tension, solvers temperature. That's like very key part of the phenomena, and whether or not like they incorporate gravity, and also like whether or not they could really experimental data.
Okay, thank you so much. It's time for a question from the reviewer. Go ahead.
In short, can you, to the reporter, in short, can you please list your parameters and their effect on the phenomenon?
So first of all, I have a ground uniform in order to show what will happen when the oil is silent. So then I provide the viscosity with oil and silicone.
But just in short, like the parameter and its effect on the phenomenon and the output.
So different oils and silicone oils to measure the viscosity because it affects the velocity. Also temperature difference, temperature gradient, the thickness, when it's no heating, what will happen, and also what will happen when the pool pan is in the uniform temperature.
Reporter, do you agree? Opponent, sorry, do you agree with the explanation given by the reporter?
No, like so for example, just now they were lacking surface tension, which is actually like the main force driving like the oil flow phenomenon.
Back to the reporter, could you please explain a little bit in your presentation what you mean by not fully relevant inertia? You talked about it briefly on slide 4. Could you just please expound on what you meant by that?
When the Reynolds number is big, when the Reynolds number is big, I will have non-laminar float. So that's why the Reynolds number has to be smaller than 1. Also, when it decreases, when the graph is exponentially decreases, the temperature difference creates the.
Thank you, that's enough. Could you please give an explanation as to why the inertia is not fully relevant?
So like I'm not entirely certain what exactly they meant by inertia, and like as you mentioned, like they didn't really elaborate that in the slides. But like I believe perhaps they were referring to like the gravity term, which they incorrectly
Thank you,
selected.
that's good. And just last question, how do you both characterize the heat flux? Because it was a little bit unclear from the discussion what your characterization is. Just very short.
We discussed the flux
characterized as like a point with the radius approaching 0 to the top.
Thank you so much. Time for preparation for the reviewer. Okay, go ahead.
Hello, today I'll be reviewing problem 4, oil flow. So just to summarize the presentation, from what we could tell, the reporter was investigating temperature-dependent viscosity in the phenomenon and in the oil, and through certain equations identified a term for outward flux, and was also using Navier-Stokes equation to describe the motion. They used the thin film approximation to further develop their model, and also made a comparison between different dimensionless constants in relation to the phenomenon. Their experiments, for their experiments, they used the CREFPAN, and from what we could tell, the parameters that they varied were the type of cooking oil, or in this case, the type of oil, as cooking oil was maybe or maybe not used, the temperature of the oil drop, and the thickness of the drop. The pros of the presentation were that some of the effects, some of the qualitative effects were considered. However, we would have liked to see a more qualitative justification, and although they were discussed briefly in the discussion between the opponent and the reporter, we still don't understand both of their, well, mainly the reporter's opinion on the effects and the relation, in my opinion. And yeah, but we do believe that the film approximation is valid for the phenomenon, and agree with the reporter's use of it in the model. The cons of the presentation were that, again, these effects were not really compared to one another, like which one was more dominant. There was mentions of the Marconi constant being superior at one point, but it was still not compared in detail. The scientific communication was quite lacking. At there were one point a lot of things on the slide, and they couldn't really understand what the reporter was talking about or explaining at the moment. The equations were not justified or explained in any way. Some of the equations were just skipped. We believe that the metal surface used was not flat, and the oil was not centrally dropped, which we could believe could alter the phenomenon and alter the results. At one point, the reporter did disagree with her own presentation with a certain boundary condition on one of the slides, and we believe that just kind of takes away the validity of their model if they're disagreeing with the theory itself. And we didn't really understand how the dimensional constants compared with the results. To talk about the test fulfillment, we believe that a thin layer may or may not have used. We didn't really get a justification of what was thin or what was not, and how is the thickness actually varied other than the ruler, which was claimed to then be an old method. The problem with the formulation states that cooking oil had to be used. Cooking oil was maybe used, but it was also like silicone oil was also used, which is not used for cooking. And there was like some form of qualitative analysis. Therefore, we do believe that some form of the phenomenon was investigated. However, the flat metal surface was not verified, we don't believe that a crepe pan could be a flat metal surface, even if any like levelers were used, and parameters were not sufficiently stated or explained in the report. The opposition, we believe that it had a good summarization of the presentation. It talked about what theory was what the theory used by the reporter was, and where it was where the presentation was lacking and where it wasn't lacking. And we believe that they had good time management in splitting up between theory investigation and talking about the points that they wanted to bring up. However, we do believe that they considered that part of the task performance complete, whereas we did not, the cooking oil versus silicone oil thing. And in the presentation, we talked a lot about they asked for justifications, and we don't believe that in the discussion they were brought up. To analyze the discussion, the opponent asked about viscosity of surface tension and how it could be measured uniformly, or it could some form of integration method could be used to vary the thickness. We believe that this is a valid, these are some valid points to bring up. However, the reporter answered a little bit unclearly. For the second point, the opponent questioned the characterization of heat flux and described it as a radial point moving outwards, whereas the reporter used some form of capillary gravity clause to define it. We agree with the opponent because the reporter doesn't account for surface tension, and it's quite a simplistic explanation. And if the model allows for an axisymmetrical solution, the reporter said yes, the opponent said no, and they disagreed with the theta term used to justify it. And we do agree against the opponent because of the simplistic justification by the reporter. Thank you.
Thank you so much. So we have 2 minutes for the concluding remarks of the reporter.
Okay, thank you all. In conclusion, sorry for delivery issues. I want to sum up all my presentation. We have investigated parameters such as viscosity or the type of oil. Actually, it's not the 2 parameters that's compared with each other. That's the 2 different experiments with 2 different graphs. So we have used the silicone oil because it's much more cleaner than the cooking oils. Then I built the theoretical model accounting for Marangoni effect and the relevant convection. Also, we've tracked the velocity of oil preferably by the model that I have shown with this particles and the temperature, gravity. And also, we also had an aluminum powder in order to see how the flux is moving. Also about the dimensionless analysis numbers. Actually, firstly, by theory, I've considered which one is more important ones. So that helped me to create my experiment part. And after that, with all of those data, I've calculated the dimensional analysis, which proved my theory fully and the model that we have this strong thermocapillary flow, that we have the laminar viscous flow, that that the surface tension dominates. So that's why the Marangoni is the most important one. Also, the review said that I have not used the center. However, in my experiments, I was using the most heated point. So as I said, the pan is not fully symmetrical. So that's why there is the temperature gradient does not start from the center. For example, the most heated point could be here, and that's why I've put my oil into this point.
Okay, thank you. Time is over, so thanks a lot to all the participants. So we have time for a jury question right now. So I will open this part, 5 minutes. Who would like to start? So someone.
Okay, to the reporter, I have a question regarding the experimental setup. So it's not clear to me, how do you actually place the oil in the pan and how do you heat it?
So first of all, I have a heater. I plug it in, and then by temperature, I serve what was the most heated oil, and also the temperature had the temperature surface. By that, I think that was near the pan, somewhere here. So that's why I had a coloration between the temperature. So I've used the glass thing. I put the oil in it with different volumes, and after that I was pouring this into the heater center from the same height. So that's why everything was controlled.
Okay, so you heat it first and then pour the oil in?
Yeah.
Okay. Frank.
I think this was on slide 8, but you mentioned in your dimensional analysis that the Marangoni number is most important. So my question is, how did you draw this conclusion from your analysis?
So first of all, the main idea is that the temperature gradient creates the gradient in the surface tension. So that's why the oil flows from the hot center to the colder ones, because the colder ones have the most stronger surface tension. And after that, could you please repeat your question?
So how do you conclude that the Marangoni number is the most important one out of
So yeah, we have the surface tension. That's the main thing in my theory. And the Marangoni number truly says about the temperature difference and how the surface tension is affected by this. So because the task was to investigate the oil on the heated surface, we do have the temperature gradient, and everything is up to the Marangoni effect.
Okay, thank you.
Any further questions? Oh, go ahead.
I wanted to ask the opponent, do you think that a non-stiff pan is a metal surface?
No, I do not think so.
Okay, another one over there.
Could you go to the thin film equation you used?
Sorry?
Sorry. Like, if anybody else has a question.
Okay, I may ask a question to the reviewer. Can you just tell shortly what you consider as the own contribution of the reporter? The most valuable own contribution of the reporter? What do you...
I believe, from what we could tell from this presentation, the most valuable own contribution of the reporter was modeling the change in temperature to the change. There was a certain simulation due to relating the radius to the temperature, I believe, and I think that was quite original. So that's the most, from what I could tell.
Okay. So,
Yeah. If you could bring the laptop here to show me the thin film equation.
oh,
Yeah, this one. Thin film approximation. So I said that when the thickness is divided by the volume, it's much larger than 1. So we could say that my velocity is much larger than so my velocity on the horizontal part is much larger than the
Okay, so the main question I have is, do you assume that there is no slip at the wall when deriving it?
there's what does
Yeah, you have the treatment here, no slip at the wall. Like, does the liquid move near the wall?
so yeah, I say that the slip condition is equal to 0. So
So
my
basically
food is
the
moving
liquids-
like by the Z coordinate.
Okay, so basically the contact line would not move.
Yeah.
Okay.
Okay, thank you so much. The time is over, so thanks a lot